Now that we are past test 1, we are moving on to some new information that we're going to be approaching at a nice steady pace. 5.1 does not have any book work required, only the online homework, but I do advise that you look through 5.1 in the book because I think that the lesson that is presented there is helpful for understanding what we're trying to accomplish here. So in this homework in this video rather, I will be working through homework 9. So for question number 1, we are given a sine value. We are told that the angle A is in the 4th quadrant, and we are required to find cosine A and tangent A. Now the purpose of these problems is not to be drawing a triangle and using SOHCAHTOA, but instead to practice the use of the fundamental trig identities. And you will find these in your book on page 197. So what we want to do is we want to find cosine using this Pythagorean identity, and then after we find cosine, we will find tangent by using the quotient identity here. So first, the Pythagorean identity that we need is sine squared A plus cosine square A is equal to 1. We replace sine A with negative 4/5. Negative 4/5 squared plus cosine squared A is equal to 1. Of course, negative 4 over 5 squared is 16 over 25. We're subtracting 16 over 25 from 25 over 25, which is 1, giving us cosine squared A is equal to 9 over 25. Now we take the square root of both sides. Now when you take the square root of both sides using the square root property, there occurs this plus or minus. Now we need to think about this. Cosine is going to be the x direction, and we are located in the 4th quadrant. So in the 4th quadrant, cosine is positive, which means that we're going to be selecting only the positive value here. So then cosine of A is equal to 3 over 5. So once you get your cosine value, then we're going to be using the quotient identity that the tangent of A is equal to the sine of A divided by the cosine of A. So the sine of A is negative 4/5. The cosine of A is positive 3/5. So that means that the tangent of A is negative 4 over 3. So the purpose of this is not to be drawing triangles as we would have in a previous chapter, but instead to practice using those fundamental identities. Returning back here, you can see the values that we arrived at, 3/5 and negative 4/3. Now moving down here, we have tangent provided to us, and we need to find cosine and secant. So what we want to do is think about what sort of identity is going to give us a tangent squared. Tangent squared plus 1 is equal to secant squared. So this is the Pythagorean identity that we want to use in this problem. So here with question 2, we are provided with tangent. We are told that tangent is, the angle A is in the 3rd quadrant. And so since we need to find secant, we're going to find this identity that includes both tangent and secant. So we replace tangent of A with 3/4. Now when we add this together, this is going to be a 9 over 16, right? And this is a 16 over 16. So that means that we have 25 over 16. Very nice numbers here. And now we need to use the square root property. take the square root of both sides. Now, here we pause and ask ourselves, in the third quadrant, is secant going to be positive or negative? Well, since cosine is negative in the third quadrant, that would make secant negative. So we're going to be selecting the negative version here, and we say that secant of A is equal to the negative value 5/4. Of course, then to get cosine, that's really easy. Cosine is the reciprocal. Cosine of A is negative 4/5. Again, the purpose of this exercise is to just get in there and use the identities and become more and more comfortable with the identities, because we will be spending a lot of time with them in the coming lessons. So back to the screen, here are the answers that we arrived at. Now let's look at question number 3. Question number 3 says that we should simplify this ratio and write the trigonometric expression in terms of sine and cosine. And though it turns out that most problems have alternate versions, question 3 does not have an alternate version, so I will not be doing question number 3 for you. If you watch the video, though, you will find that there is an example provided for you that is analogous. This is the 1 plus sine theta over 1 plus cosecant theta, and you are then going to do the same process for your problem as the video. Okay, so question number 4 also does not have alternate versions. So what you're going to be doing is replacing tangent and cotangent with sine over cosine and cosine over sine, respectively. And then you're going to simplify that complex fraction. Question number 5. In this case, what you're going to do for this problem, tangent squared minus secant squared, is you'll come over to the Pythagorean identities, and you'll see that there is one that involves both tangent squared and secant squared. You can do a substitution of secant squared or tangent squared using this identity, but what you want to do is simplify down to just a single trig function. Okay, now, number 6. I will be doing both questions 6 and 7 on the board here. What we're going to be doing is taking each of them and simplifying them to a single trig function or a constant with no fractions. So here, question 6, what I want to do is I want to replace either tangent or cotangent with something using one of the fundamental identities. Now, in the fundamental identities, let me flip back to those for you. We have that tangent is sine over cosine, and cotangent is cosine over sine. So we can either replace both tangent and cotangent and have a sine over cosine, cosine over sine, or alternatively, since cotangent is just equal to 1 over tan, or tan is equal to 1 over cotangent, you can replace just a single one of those, which would be a little bit more efficient. So back here, I would replace cotangent and by replacing it here, now I have tangent over tangent. Is equal to 1. Now you may have wondered, why didn't I skip this step? Isn't it obvious that tangent t times 1 over tangent t is equal to 1? Yes, it is, but what we're doing here in 5.1 by simplifying expressions is you are warming up your brain, giving yourself habits of mind that are going to prepare you for 5.2. And what we're going to be doing in the next lesson is proofs. Now, not the proofs that you did in geometry where you had to state the next line and then give the postulate or theorem, but instead we're going to be doing a bunch of algebraic substitutions, one small step at a time, because you're going to be given the beginning and the end, and you need to prove that what's on the right-hand side of the equation is equal to the left-hand side of the equation. And you do so through a series of very small steps. So while I'm simplifying, I'm going to be going extra slow to show you the same kind of small steps required in a trig proof, okay? It's called verifying an identity. If you don't like the word proof, verifying an identity. Okay, question 7. So I have that secant is equal to 1 over cosine and tangent is equal to sine over cosine. So now I have a complex fraction. And this complex fraction is going to reduce to 1 over sine, which then would simplify, because we want to have no fractions in our final answers, to cosecant of t. So we just keep going back to that page. In your book, it's page 197 that has that green box full of all those fundamental identities, and you do as many substitutions as you need to get down to a simplified result. So here we see question 6 reduced to 1, question 7 reduced to cosecant t. Now, question 8, we are simplifying this fraction to an expression involving a single trig function with no fraction again, and also the same directions for question 9. Questions 8 and question 9 are very similar, so I will just be doing question 8, and then I'm going to jump down to question 10, where we again are going to be simplifying to a single trig function with no fractions. So going back to our Pythagorean identities, sine squared x plus cosine squared x is equal to 1. So that means that for this right here, I can replace the numerator with 1. And then 1 over sine, going back to those fundamental identities again, a 1 over sine is going to be cosecant. So a 1 over sine squared is then cosecant squared. And that's it for that one. Now, question 10 involves these negatives that are inside. This goes to the concept of that some functions are called odd functions and some are called even functions, and then some functions are neither odd nor even. But when it comes to trig functions are going to be odd or even, and cosine and secant are even, and sine and tangent are odd, and they're reciprocals. Now, what does that mean, odd and even? Well, one of the things it means in these even-odd identities is that for an odd function, if you have a negative inside, the negative will pop out in front, okay? So the negative does not stay inside here, you can pull it out. You can see that this is going to be happening for sine and its reciprocal, tangent and its reciprocal, but not for the middle two. The middle two are even functions. Now, let me point out that we are familiar with some other odd and even functions. For instance, the function y equals x cubed is an odd function. And this is helpful to remember because it has an odd exponent, or easy to remember by the fact that it has an odd exponent. So if we were to look at f of negative x, if this is your f of x, if you put a negative x inside the cube, what happens to the negative sign? It comes right out. Okay, that's how odd functions behave. The negative does not stay trapped inside the function, it comes right out in front. Now compare that to an even function. A very familiar even function that we know is y is equal to x squared. Also, the absolute value function is an even function. Here we have an even exponent. Well, if you're looking at this one, f of negative x the negative goes inside the function. And what happens when you square a negative. You end up with no negative anymore. The negative dies. Okay, so that's some properties of odd and even functions. Another thing that is going to be true of odd and even functions is that odd functions have what's called point symmetry, or 180-degree rotational symmetry. So think about the graph of tangent and the graph of y equals x cubed. Depends on whether your arrows keep going to the left and the right, if this is going to be considered a x cubed here, or if you had asymptotes, you might think that this is a tangent graph. But either way, if you rotate this 180 degrees, you have point symmetry. This graph is exactly the same as it was if you rotate it 180 degrees. And that is true of any odd graph. If you take sine, or cosecant, or tangent, or cotangent, and you rotate the graph 180 degrees, it will look identical. So odd graphs, odd functions, will always have what's called point symmetry, 180-degree rotational symmetry. And you can compare that to even graphs. Even graphs have a symmetry as well. Their graphs are going to be symmetrical in the same way that a parabola is symmetrical. Remember that a parabola is going to be symmetrical about this axis in the middle, right? And so we have this reflection. There is a reflective symmetry across the y-axis.